So this is just a run of Dijkstra's algorithm, and we've already done it. So I'm just going to breeze through this. And now I think, yeah, so let's find the shortest path from A to D. Now all we want to find is from A to D. So once you make these labels permanent, you can stop. You don't have to go further than that. So give this a try. Write it out as a table like this.
Okay, sorry. There it is.
Anyone know what it is?
6 from C.
6 from C. Yeah. So let's. No, even it's okay if you haven't finished. Let's get started. Let's do this. So I will just write the table underneath. So A. Okay. So step 0, A is the source. So that's 0, a nil value, and everything else is infinity. Okay. So this is undirected. So you just traverse edges in whatever order, whatever way you can. So what are the neighbors of A?
B, C, and E.
B, C, and E. So what's B going to change to?
3, A.
Yeah. All right, so I better put a box around A. That's permanent now. That's a permanent label. And B is going to now be 3 coming from A. C is going to be 5 coming from A. E is going to be 3 coming from A. And E is still infinity. Okay.
3 from A.
Oh, did I do something? Oh, yeah. I'm afraid to hit the erase button because it will just trash everything, so I'm sorry. Pretend like I'm writing in pen. All right, so that's 3 from A. So now, what's the cheapest?
B.
It's a tie. So let's just pick B because we're stupid. We'll pick B.
Yeah.
Hmm? Oh, did I do something? What?
E is 3A.
Ah. Okay, you're right. Sorry. E should be. Thank you. All right. Boy, we really are stupid. Okay, I guess. All right. Good. That works. So that's 3, and that's from A, and that's still infinity. All right. So what's the cheapest? You think E? Let's do E. I think it doesn't. We're going to make one label permanent and then the other label permanent right afterwards. So it doesn't really matter. So let's do E. So E. What is adjacent to E that's not permanent already? So I don't look at A again. I don't go back along that edge. Okay. So the edge from E to B is 2. E is 3. So 3 plus 2 makes 5, which is bigger than B's label, which is 3. So no update there. So that stays 3A. All right. C, 1. So 3 plus 1 is 4. That definitely works. So that's going to be revised downward. And I now say E. That's where oh, yeah, I need to make that permanent. Okay, so that's not permanent. How about D? 3 plus 4 is 7. So that gets revised to 7. Coming from E. Great. All right. What's the cheapest?
B.
The lowest label is B. So I make that permanent. And going out from B, A and E are already permanent, so I look at C and D. Well, D's not reachable, so just C. So what do I get for C?
So 4.
So 4. C is already 4, so it's a tie. You could switch the parent, and it wouldn't hurt. You'd still get an optimal path, but the algorithm just says, no, don't bother. Just leave it. So C stays 4E. How about D? Well, D is not reachable. D is not a neighbor, so I just copy that down. And now I'm running out of room. Okay. So now what?
4 is permanent.
4EC. So now the only edge left to a temporary label is D, which is 2. So 4 plus 2 is 6, which is less than 7. So this updates to 6 from C. See that? And now that's permanent. Okay. So in fact, the D was the very last thing we made permanent. So in fact, we got distances to everything else as well. All right. Questions? Okay. Great. Moving on then. Oh, break time. Take time. We'll do Floyd's algorithm.
I think so.
They should have one too.
They do, like $20.
Yeah. Well, if you go to the commissary, you can up for
Yeah.
I got $1.50 at the shop.
They do the 4-pack?
I don't just sell myself. That's the nose first into my keyboard serious. Now I wake up at 3:15 in the morning, so it has nothing to do with computing stuff. So if it does happen, don't worry, it'll wake you back up.
Oh, okay, fine.
I don't think I should be sleeping anymore.
Quite interesting we saw her.
I was having a conversation with the tech morning. It was like, man, your PT, whatever. I'm like, yeah, but you've got a wife. You can, there's limitless bounds after you put the ring on her finger. You can take shove pies in your face. The expansion can become great. I was like, until I can feel it.
How are we talking to PT about having a wife?
Because Tommy's like, yeah, PT's for the birds. I'm like, yeah.
Too mad about
Yeah.
you're going to PT.
I was talking to PT. Yeah, you're already married to the army.
The concept doesn't occur when we were just talking about that.
Yeah, dramatic.
Then I was really should sleep.
I should really sleep so I can tell funnier stories.
You know what? Let me know essentially how it works out for you when you get married and you finally put that ring on her, and then you throw pie in your wife's face. I want to know how that works out for you.
Oh no, that's not
That
throwing it in
will
my
work
own
at all.
face.
That will work.
I want to know. I want to know if you wake up the next morning like bald and all kinds of craziness happening. Yeah, I really like to know.
No, I think I'm starting to come down to something.
You know what I just found out about the Well, we have to go in at 5:30 on Thursday. So hot trash can get after the test if you feel like.
Yeah, no shit.
Have your wife right. That means it's these are gonna start like drinking. Like what a terrible.
Son, Thursday is going to be liquor or beer. I don't know how else it goes.
That's sometimes.
Well, you're not going to know, so you might just want to mix it.
No, you'll have a feeling,
You'll
man.
know.
I'll counsel myself not to come to that formation.
I think it's gonna be like.
I'll just counsel myself not to come to that formation.
I
Either
think
What
that
are
or
they going to do? They going to tell you you can't sign out?
yeah.
that is true.
All right,
I got an approved leave form.
I get a drunk on duty. 'Cause
Absolutely.
I will be.
I'll be up here between 6 and 9. Sure.
Yeah.
FA24s are all going to the cowboy club or whatever that is. They're going to be fun. Yeah. Just tearing it up.
I think the test will be like quizzes.
This is what you get for making us go to CIB.
I'm still gonna be like,
So, sir, do you think we're going to
if
see
you turn it in again, trying to like look at the page in front of you, like,
breath?
Bread first.
Breath first again?
that would be awesome.
See breath first again. You'll see it on the homework. You might see it on the test.
I was going to. Yeah, bread first.
Yes.
You didn't get that? Okay.
Dude, don't listen. You don't have to listen.
No,
You can choose. I gave you cough drops.
Okay.
It's like a prison system, sir.
I see that now. Yeah.
But you're talking about, say you've got a pen that doesn't work.
Green or red? It's Christmas time.
There we go. So you have this one, and you go into do
I remove myself,
Or Arnie.
This breath first?
Roger, sir.
Okay. Yeah, I kind of sketched through breath first. I didn't go through. Yeah, I didn't do
You have all
details
these
in
other.
there.
You can have different offshoots. You can have the X and Z. When you were talking about actually using the cue, so you've got a cue down here. The first thing that you're going to do, the way it was always told to me is it's like grabbing this, having a pull here, and pulling it through. It puts and it puts all the different nodes in order.
Yeah, I could. Yeah, that does it.
When you know R, that's your root, and you put the children in next.
Yeah.
Shove all the children in the bin.
Children are going to come first.
There you go. So they come in. The moment you get done getting them, you get that guy out. You're going to notice that your root is always going to have a distance 0, and then each one will have a 1.
Yeah.
Because it's that next hierarchical view. Right. And you'll know it the moment you pull that guy out. That's all the zeros. These are all the ones. And then you start again. You can
Like register actually makes sense.
You go
I
T.
know that, but triple R is
just randomly selecting.
random phrase.
Well, randomly selecting is effective. But once you put it in the queue, you have to go in order.
Yeah.
So we got T in there. You said, okay, now that we have T, we'll go ahead and add WX. W and X. And we know that we have to add one.
I don't ever sound
distance,
off with
whatever
the
node.
I'm just saying.
We just
Yes.
Register was actually
Yeah.
two, and you just keep doing that in a search, a breadth first search. Like if you were looking for W, you just found it right there, and you know that it's
Right.
distance two.
Right.
And then when you said doing the backtrack to it,
Yeah.
that would just be this guy, this guy.
Yep. Good. In fact, Dijkstra, if you look at Dijkstra, where all the edge weights are equal to 1, then it's exactly this. It's exactly this.
Well,
You're always pulling out this. You're pull out the smallest smallest
I
distance.
show this up, I'm like, okay. I mean, take away
well, it's going to be the only
Yeah, each
weight that you have.
right. Each label is just going to be what it gets initially. Is never going to be updated, and eventually it'll just sit there until it's made permanent.
Well, the way I always think about it is the linked list format with the object. You have the parent, the child, and assigned distance. Hey, you know what? Now I'm going to do it in microseconds. That's right. That doesn't even matter here, but I'm going to do it. And I'm going to assign random values until Jerry's head explodes. Because that's what I think is fun, and that's what I want for Christmas.
Again, your thespianism is coming out the way that you are taking the stage right now.
I don't know why Wayne is yelling.
Thespianism. I'm going to add that to my list of things to serve as a pond.
Yep.
Yeah, he's it's amazing that it's like painted on top of like they videotape the actors and then they painted them. Was that good? It was one of those movies that I don't really think. No, I didn't know what to expect going into it. It was like half decent.
What movie?
Standard Darkly.
I never watched it. I remember when it came out though.
It's not uplifting.
That's why I didn't see it because
It's also not really like train spotting level or what is it, a really depressing one?
No
Spotting
Book?
for a Dream. Yeah, it's not that bad.
Notebook?
I've never seen it.
Dude, I'm gonna tell you right now, if you watch the Notebook and you don't get a little choked up, you're
So what do you
you're
say?
heartless.
Because I laughed.
You're heartless. I did it to keep from like paying attention. She started crying, and I was like, man, that sucks. I was like, no, I'm gonna make fun of you so I don't get upset.
I was waiting for the older guy to just wake up and be like,
Yeah. That's why I was like, you leave me. I was like, probably. I tried to like.
I didn't tell my wife, I was like, hey, if I get Alzheimer's and I don't remember you, fucking
bounce. Yeah.
shut deuces.
That's what I told her. I want you to
I'm not going to remember.
wasting your time for an hour a day.
My wife didn't say it back to me, but I took it to mean that she did.
I'm with you on that one.
Skip me a deuce, skip me a gander.
She called me a dick when I said that. I was like, it would take a couple weeks. And I was like, okay.
Yeah, but in my family, it's always the guy that goes. We never do the last choice.
My parents have lived surprisingly long.
Oh, I mean, considering alcoholism and all the smoking, all the males.
My grandparents came like early because of between alcoholism and smoking.
Yeah,
And fatness.
My dad too.
Oh, we know about this week. All we ever have in our hand.
I'm the smallest. I'm the skinniest guy in my family on one side for like probably 5 generations.
So when you retire,
Except for my grandpa himself. But I think he was so skinny because he did liquid diet.
that usually helps because alcohol.
Dude, you can do the beer diet if you do it right and lose a lot of weight.
Yes, but
All you can.
that's all you can
Yeah.
have too.
It's effective.
Coming to work, drinking.
You still like beer? Sure. I'm on a diet.
Do the beer diet with like a multivitamin and like some soy protein. You're golden, man. You got everything in your son.
Otherwise you'll
I
pass
don't know
out.
about golden.
Arrested,
You
like
want
every
iron in somewhere you can
That's
collapse.
what I'm saying, the multivitamin.
Yeah, but
and you need some protein.
They're laughing at you.
He at least would be gold.
You have vitamins B, E, E, and R right there. Sorry, that's Kansas scoop.
I thought you were going to go with ALE.
There you go. Yeah, something all of those in one place. I feel a lot. Tears and something.
What's up?
If you, I don't know what it is with these, but if you can have more than 3 now, check your world.
It's probably written on the back.
That's small, right?
I think my kid is like my health system kryptonite because I've been sick more times since we've had him than I was in like the 7 years we were married beforehand.
Does he go to preschool anyway?
No! Like, where are you getting this?
Because I believe it's the more you're out in public, because for the last 2 years or so, my wife was trying to find a new guy. She never got sick. And I got like the usual like once or twice a year. So, and I wouldn't even make her sick. She would just be like, oh, you see me, and I'm just waiting to see her in that shower. 500 people, because she like constantly actually you're getting sick.
Sucks. And then also you're gonna start coffee.
Now you got your basically like. But I got my. Who knows what was in that thing? So don't worry about it. She didn't. She was like, oh,
That's a blue shot?
Yeah.
That's not good, man.
I gotta think of something. I've got
I
to
need
do
to
something
get
to
it.
do that day.
I'm not going to get it.
they were allergic to
I'll give you that lie. I think I'm going to do it for the Army.
He refuses to get injected.
I'm not gonna make food.
I think
That's a new level.
now that I've been starting to get sick because of my kid, like I'll start going ahead and get it. But I mean, I've been for like the last few years. I got sick like once every 3 years. It seemed like.
Sorry. All right, let's get going.
According to the Army, I am.
All right, here's another one where it's fine. You can look at the code. You might even be able to implement it. That's fine. But I think just to get understanding what's going on in Floyd's algorithm, it's good to just go through an example. So Floyd's algorithm is finding the shortest distance as well as a way to construct the shortest path from all pairs of vertices, sort of at once. Okay? And it uses a technique called dynamic programming to do this. What you do is you have a table. It's a two-dimensional. It looks like an adjacency matrix. It starts off looking like an adjacency matrix, but then you update the table step by step. And if there are n vertices, you do this in n steps. And eventually, what comes out is the table of shortest distances. So you start with the table of edge weights at the beginning, and eventually you wind up with the table of shortest distances at the end. So here's the idea. So if I have, first of all, I'm going to arbitrarily label the vertices 1 through n. So the vertices, I'm just going to give them numerical labels, 1, 2, 3, 4, up to n. All right, so n vertices. suppose I have two vertices, I and j, and some path from I to j. Well, this path is going to go through maybe some intermediate vertices. I'll call the vertices in between, not including the endpoints, I'll call these intermediate vertices. Okay, so here's what we have. We have an n by n matrix, D naught, to start with. From D naught, we construct another matrix, D1. This is also n by n. In fact, these are all going to be n by n. Go up through all of these until you get to D sub n. This is n by n. So, starting with dk for some k, you then compute what dk plus 1 is going to be. So, I'm computing one matrix from the previous matrix. So, I'll tell you what d naught is, and then I'll tell you how to get dk plus 1 from dk. And then you just repeat that process until you get dn. And when you get dn will be the matrix. It will be the distance table of shortest distances. Okay. So at the moment, let's just compute distances. Let's not worry about the actual paths. Okay. Let's just compute shortest distances. So here's what dk is. So the ijth entry of dk looks like this. Let's call it this. This is the shortest path equals actually the shortest distance. Shortest distance from I to j, where all intermediate vertices are constrained to be k or less. So, vertices are labeled 1 to n. So, what's this saying? What this saying is this is going to be the shortest distance on some path you can go from I to j, where all the intermediate vertices have to be among the first k vertices. They can't go outside that. All right. This kind of sounds a little artificial. For one thing, you can label these vertices any way you want to, as long as you label them 1 to n. And you'll actually wind up with the same table. But let's just pick an ordering and go with it. So so this is the key. This is the key to the whole thing to show to see why this works. So here's what you do. First of all, let's look at d naught. D0. I'm going to erase this. I'm going to have to erase something. Well, I'll write it up here. D naught. Well, what is D naught? It's the shortest distance from I to j where all the intermediate vertices are less than or equal to 0. Well, the vertices start at 1, so there are no intermediate vertices that are less than or equal to 0. So what this means, this is the shortest way you can get from I to j with no intermediate vertices. In other words, the only way you can do that is with a direct edge from I to j. So this is the edge weight of the edge ij. Or this will be infinity if no edge. If there's no edge in a graph, just make it infinity. So you can't You can't go directly from I to j. So D naught ij, that's the only way you can go from I to j with no intermediate vertices is to follow a single edge. Okay. All right. Okay. So this is really given. This is the input. Okay. This is how you would specify the edge weights. You just put them in a matrix, and that would give you the edge weights. So we'll go through an example when I get this done. So now, suppose we have dk for some k, and we want to find dk plus 1. So suppose dk ij, I don't know, let's say is equal to 10. So at this point, that means that from I, from I to j, let's say all the vertices down here are less than or equal to k. So we know that there's a path. And in fact, the shortest path that only uses intermediate vertices less than or equal to k, this path has length 10. So let's put some edge weights on it to make it length 10. Maybe that's edge weight 1, 2, 3. That gives you 6, 2, 2. Okay. So here's a situation at k. We've gone up to k. We've allowed intermediate vertices up through vk, 1 through k. Now, to get dk plus 1, we have to consider what happens when we allow dk plus 1 to be an intermediate vertex. That's really what we have to do. So dk plus 1 ij is like dk ij, but allow k plus 1 as an intermediate vertex. So where is dk plus 1? Well, where's k plus 1? Yeah, it's up here somewhere. It's above the dotted line. All right. Now here's the thing. dk plus 1 might equal dk. Or it might be shorter. Because now I'm allowing a vertex I didn't allow before. So how do I know if it's going to be shorter? Well, what I do is I look at the distance from I to k plus 1 in dk. And then I look at the distance from k plus 1 to j. If the sum of those two is less than 10, then I found a shorter path. Because if I go through k plus 1, and I don't go through anything bigger than k plus 1, what are the intermediate vertices? Well, the path is going to start at I, it's going to go down below k, and then at some point, it's going to hit k plus 1, and then it's going to go back down again. From k plus 1 to j, it can only hit vertices less than or equal to k. So I have two possible paths. I have the original path that I had that does not go through k plus 1. But now I consider what is the shortest path that does go through k plus 1, and that's going to be what I get from dk I k plus 1. That's going to tell me what that distance is on that segment. and this is going to be dk, k plus 1j. That's going to tell me what that distance is. If that distance is shorter, then I need to register the fact that the shortest path now goes through k plus 1, and I need to dk plus 1 ij is now going to be less than 10. So here's where that might happen. If that's a 1, and that's a 1. So this edge going here is a 1, and that edge coming down here is also a 1. Look what happens. Now what's the distance from I to k plus 1? 4. 1 plus 2 plus 1. And the dk distance from k plus 1 to j, 1, 2, 2, that's 5. So now I have a path of length 9, a path of length 4 up to k plus 1, and then another path of length 5 from k plus 1 to j. That gives me a total path of length 9 from I to j. So dk plus 1 ij, I revise downward to 9. Does that make sense? Okay. Now, if this didn't happen, and the sum of these two numbers was at least 10 or bigger, then there's no reason to do any revisions. I'll leave it at 10 because I know that, and I know there's a path that 10. It just says there is a shortest path that does not go through k plus 1. All right, ready for an example then? Yes. Yeah, I thought so. Let's just glance at the algorithm and see what it says. So the dk plus 1 matrix at ij is I take the minimum of the original dkij and the sum of dk of I k plus 1 plus dk of k plus 1 to j. So these are the two segments that might go through k plus 1. And if dk plus 1 is less than dk, I'm sorry, if I do a revision downward, I'm going to record that back in a separate matrix. I'm going to set that equal to k plus 1. That's saying I found the shortest path from I to j that goes through k plus 1. But that's a separate matrix. Don't worry about the p matrix yet. Okay, let's just go with the distance matrix. Okay, and I just keep going until I get to the end. And notice when I get to the last matrix, dn, that's allowing all intermediate vertices, 1 through n. So that's going to give you the shortest paths. That's going to give, because they're unrestricted. All right, let's do an example. I got to erase this, all of this. Let's just have 4 vertices. Any more than 4 gets pretty unwieldy pretty quick. All right, let's put some edges in. That's a 3. That's a 5. Maybe that'll be a 6, and I don't know, maybe a 2. I'm kind of making this up. And this will be 9, and let's see, what else? Now I'll make it strongly connected so all the distances will be finite, so maybe I need to I'll put another edge here. What shall I make that? So let's write down D0. So I'll index the rows and columns for you. So from 1 to itself, well, these are all 0. Okay, so they're going to be, in fact, you'll have 0 all of these matrices will have zeros along the diagonal because it's always the shortest way to get from a place to itself is 0, since there are no negative loops. All right, from 1 to 2, what is it? 3. From 1 to 3, 6. And from 1 to 4, 9. From 2 to 1.
Wow.
Infinity. There's no edge. So make that infinity. 2 to 3. 5. 2 to 4. Infinity. 3 to 1. Infinity. 3 to 2. Infinity. 3 to 4. 2. 4 to 1. 4. 4 to 2. Infinity. 4 to 3. Okay. That's D0. Just record the edge weights, and if there's no edge, it's infinity. So, what we're going to... So, the first intermediate vertex we're going to allow is vertex 1. Okay? So, I'm going to cordon off the first row and first column. I'll call it the magic row and magic column. This is the one we're going to compare to. So let's write, so this is now D1. 1, 2, 3, 4. 1, 2, 3, 4. All right. First off, I copy over the magic column. The magic column doesn't change. So the destination and the source and destination aren't affected if one of them is D1, because D1 has to be an intermediate vertex for that to happen. So this is going to be 0, 3, 6, 9, infinity, infinity, 4. Okay. Now let's look at and all the diagonals are 0 again. Okay. All the diagonals they're always going to be 0. So let's look at our first non-trivial one, 2 to 3. Okay. In D0, 2 to 3 was 5. Okay. Is it possible to get something shorter than 5 by going from 2 to 1 and then 1 to 3? So what's 2 to 1? That's this thing. And then I add that to 1 to 3, that's this one. Well, how I get that is I go over to the magic column in the same row, and the magic row in the same column. I add those two together. If it's less than 5, I update. It's not less than 5 because one of them is infinity, so there's no possible. So I don't change this. This is still 5. I don't have a shorter path by going through vertex 1. It's still the best way to go from 2 to 3 is still directly. I can't even get to 1 from 2. Okay. How about 2 to 4? Well, same thing. Infinity, 2 to 1 gives me infinity, and then 1 to 4 gives me 9. So infinity plus 9 is certainly no less than infinity, so that's the infinity. All right, how about 3 to 2? Let's look on the graph. 3 to 2.
It's not a direct way to get.
Yeah. Can I go through? I can't get through directly, but can I go through 1? No, I can't even get from 3 to 1, let alone 1 to 2. So that's still infinity. So that's still going to be infinity. Nothing's changed yet. How about 3 to 4? Yeah, it's still 2 because this is infinity. So this is still 2. So here's the trick. So update in the next matrix, you look in the previous matrix, go across to the magic column and go vertically to the magic row. Add those two numbers together. If it's smaller than the current number that's there, you change it. That says you can get there shorter by going through this magic vertex, this magic intermediate vertex.
Can you explain that again? Just how do you do it again?
All right. So for each blank entry over here, go to the corresponding entry over here.
Right.
Look at its value. Go across to the magic column and go vertically to the magic row.
Mm-hmm.
Take the numbers you see there.
Yeah.
Add them together. If that number is less than this, then you update this down. Right? So we're updating things. We're only updating down, just like with Dijkstra. We're only updating down. So 4 plus 3 is 7. That's definitely less than infinity. So that's now a 7. And notice that makes sense, right? To go from 4 to 2. To go from 4 to 2. I can't get there directly. D naught, but I can go through 1. I take 4 followed by 3. Okay, so that gets updated to 7. Now I have 1 left. 4 to 3. Does this? Yeah. So 4 to 3. 4 plus 6 is 10, which is less than infinity. So this changes to 10. All right. What changed down here? The only thing that changed are these two. So here's now going to throw in the P matrix. I want to record the fact that those two changed in D1. So here's the P matrix. P matrix is 4 by 4, same dimensions. It starts off all zeros. Let me write it. Let me index the rows and columns.
Back matrix. You can see it a little bit.
Yeah, P stands for path. All right, it's all zeros, but what we're going to do is we're going to record labels of intermediate vertices that actually gave us a decrease. So here, these two both used intermediate vertex 1. So we're going to change these zeros to 1. So if going through an intermediate vertex gives you something less, an entry, you go up in the P matrix, the corresponding entry, and you put the label of that intermediate vertex. Yeah, so it's currently 1. All right. So we've gone from D0 to D1. If you didn't quite get all of that, stay tuned because now we're going to do the same thing from D1 to D2. I no longer need D1. I no longer need D0 because D2 only depends on D1. So I can cross that off and reuse the space. D2. All right. 2 is now my magic intermediate vertex that I'm going to check. Can I get shorter things going through 2? So back in D1, I'll make the second column and the second row my magic column and row. I'll copy those over for verbatim. They don't change, so that's 3, 0, infinity, 5, infinity, infinity, 7. And put zeros in the main diagonal, as always. Okay, and now I just have to fill in the blanks. The blanks are going to be where vertex 2 is an intermediate vertex. So, 1 to 3. Let's look over here. So the current value of 1 to 3 is 6. If I go and I see, well, 1 to 2 is 3, and 2 to 3 is 5. Add those two together, you get 8. Well, that's not as good as 6. So there's no update. So I'll just leave that as a 6. And I don't change the P matrix at all. Okay. 1 to 4 is currently a 9. Do I get something better if I go through 2? No. 3 plus infinity is way bigger than 9. So that stays a 9. All right. How about 3 to 1? Infinity, yeah, it's still infinity. Still can't get from 3 to 1 at all. How about 3 to 4 is currently a 2. Infinity, yeah, that's not going to get anything better. All right, let's try 4 to 1. No. 4 versus infinity plus 7. 4 to 3 is a 10 versus 7 plus 5 is 12. 10 is still lower, so nothing. So vertex 2 is of no help as an intermediate vertex. Okay. So there's never going to be a 2 anywhere in the P matrix. So that's D2. All right. So D3. Well, all right, so nothing changes. Let's try D3. We know that there's going to be a finite distance from any vertex to any other vertex because it's strongly connected. So eventually these infinities have got to turn to be finite. So D3. So I go back to D2. What's the magic vertex? 3. So I'll just mark off the row and column. Copy it over. I get infinity, 0, 2, 6, 5, 0, 10, and then put in my zeros. Excuse me. All right. So to fill in the blanks, going from 1 to 2. No, I can already get there with 3 steps, and I can't even get from 3 to 2. Well, I can get from 1 to 3 by 6, but to go from 3 to 2 takes infinity. Anyway, it's all bigger than 3. All right. 1 to 4. Aha. I currently can get there in distance 9, but if I go through vertex 3, so how do I get from 1 to 4? I go 3, currently I'm going 3, 5, 2. I think that's what I'm going. Oh, no, I'm just going straight down 9. Okay, yeah. But now I see there's something shorter. I can go through vertex 3, so 1 to 3 is 6, and then 3 to 4 is 2. So 6 plus 2 is 8. That's better than 9. So that's an update. So that changes to 8. And I record the fact that I updated that this path goes through vertex 3 by putting a 3.
How did you get that? I'm not following like how you get from, D2 to D3 to value 8.
The value 8?
Yeah.
Okay. So the current value in D2 is 9.
Right.
So what I do is I go down to the magic column and row, add those two numbers together.
So 6 and 2.
6 plus 2, yeah, is 8,
Okay.
which is less than 9. Yeah. So I get the 6 by going, so I got to go from 1 to 4. That's the idea. I get the 6 by going from 1 to 3, and then I get the 2 by going from 3 to 4. That's how I get there. All right. 2 to 1. Yeah, in fact, I'm going to get infinities here, so anything in these two columns is not going to change, right? So this is still going to be infinity, and I'll even put that down. That's still a 4, and that's a 7. There's no way those are going to change. So the only thing left is 2 to 4. Does it change?
Yes.
Yeah, definitely. Infinity goes down to 5 plus 2, 7. So this now also becomes a 3. If I don't just have to update zeros. If this was another positive number besides 0, I would still just change it to 3. All right, so that's D3. Almost done. D4. All right. So now, vertex 4 is my last intermediate vertex to allow. Then after that, I've allowed everything. So now, I look at what are the numbers of going through vertex 4. These are the numbers that I get. So I copy them over. This will be 4, 7, 10, 0, 2, 7, 8, 0, 0, 0 on the diagonal. Okay. All right, so I got to fill in other stuff. All right, so going from 1 to 2, I currently directly is a 3. Indirectly, going through 4 is 7 plus 8, which is way bigger than 3, so that doesn't help at all. So this is still a 3. 1 to 3 is a 6 versus 1 to 4 and 4 to 3. That's 10 plus 8. That's 6 is still way better. Similarly, with 5 here, 5 versus 17, 5 is still lower. But now these 3 infinities are going to change. So 2 to 1 is infinity, but that's bigger than... So going from 2 to 1 currently is infinity. I can't get there. But now going through vertex 4, I can go 2 to 4, which costs 7, and then 4 to 1, which costs 4. So going through 4, that's going to cost 11. So 4 plus 7. All right, how about 3 to 1? That's infinity, but now what does that decrease to? 6. And always check back here to see that there actually is a path from 3 to 1 of length 6 that goes through vertex 4. Oh, I got to change these, right? This is now 4. This is now 4. And one more. 7 plus 2, that's 9. Question? There is our table of distances. These are the shortest distances. This is our path matrix. So in just the last couple minutes, so we won't do Maxwell. In the last minute, I'll tell you how to use the path matrix to actually recover the path. So this just tells you the distance from some vertex to any other vertex. So if you want to recover the path, here's what you do. At the end, the ijth entry of P is the maximum label of any intermediate vertex. Vertex along shortest path from I to J. That's what it is. Because whatever, because we were updated it, so the last time it got updated, that was the biggest intermediate label you could have.
Isn't this also kind of going to give you the next hop as you look at the P matrix? So like from 4 to 2, I know there's not a direct link, but looking at the path matrix, I know if I go from 4 to 1, it'll eventually get me to 2.
Yeah, so let's go from 4. Let's go from 4 to 2. Okay, so I want to go 4 to 2. So here's 4, here's 2. I look at P42. P42 says 1. That means there is an intermediate vertex somewhere along the path of length 1. Now, that might not be the only intermediate vertex. So how do I fill in the rest? Well, I look between 4 and 1 now. I look at P41 and seeing if there's an intermediate vertex between P41. So P41 is 0. A 0 means no intermediate vertex. So this is a direct edge. And now from 1 to 2, I look at P1 to 2. That's also 0. That says there is no intermediate vertex. It's just a direct edge. Maybe that wasn't such a great example. Let me try 3 to...
4, 3.
And none of this is going to be very...
Yeah, 2 to 1.
which one? 2 to 1? Let's try 2 to 1. Yeah, 2 to 1 I think is good. So 2 to 1 is actually takes more than one intermediate thing to get there. All right, so let's do 2 to 1. All right, so I'm going to erase it. So I want to get from 2 to 1. I look at P21 and I see a 4. So P21, that's a 4. Okay? So somewhere in between there's a 4. This is P21. Okay? Now to check, is there an intermediate vertex from 2 to 4? Well, for that I look at P24 and there is. There's a 3. So I stick a 3 in between these two. This is P24. And now I check all these adjacent ones. 2 to 3, 3 to 4, and 4 to 1. 2 to 3, 3 to 4, 4 to 1, they're all zeros. Which means no intermediate vertex. And so that's the shortest path. Okay, so what you just recover the path step by step by finding the biggest label of an intermediate vertex, putting that somewhere in the middle, and then checking the P matrix again to seeing if there's any intermediate vertices on one side or the other. Just checking those different entries. Keep doing that until you see 0 entries in the P matrix, and then you know there's no more intermediate vertices. So that's how you do it. All right. Good stopping point. Any questions? Okay, all right. Homework. Oh, turn this on. Homework should be posted by now. So the internet is on. And I posted the homework, and I think there's 2 shows. 2 minor shows. You got time. Fine.
Yeah, I'll print out enough for everybody because I got to open.
Yeah, I want to do that.
Everybody but Chris.
I'm taking Chuck, so
So for you, Chuck.
Yeah, that'd be fun.
Maybe.
That'd be fun.
Yeah. I think he's like the designated history guy. He's like the FNG.
Oh, that's not nice.
Stop that. Give it over all the NGs.